Good morning, everybody, and welcome to our Spectrum Library Matching webinar this morning. Before Jens starts, I'd just like to draw your attention to a couple of housekeeping items. On your console, you have a Q&A box. Please feel free to submit any questions you may have for Jens at any time during the presentation, and he will do his best to answer as many as possible depending on the time we have at the end of the slides. And also you have at the bottom on the right-hand side, the green widget, you have a resource list which gives you links to the slide deck for this presentation, a couple of web URLs, and some additional information on Spectrum Library Matching. So that said, I would just like to now hand over to Jens, who is our presenter for this morning's webinar.
Thank you, Sue. My name is Jens Rafelsen, Applications Engineer with EDF, specializing in EDF. So I'd like to say good morning, or afternoon or evening to all of you, depending on where you are, and welcome to today's webinar. Probably had time to look at the intro slide, but just in case you didn't realize, this is a webinar on Spectrum Library Matching, correlating phase map spectra with library matching for conclusive solutions. As I said, I'm an applications engineer with EDF. My background is primarily in surface science and optics. My PhD is in physics. We are going to be looking at a few minerals today. So given my background and given that some of you might have geology or minerals background, I'd like to apologize beforehand for any mispronunciations. And I know those of you in geology like to use the one with oxides. We're not going to do that today, so that's the way it is. But with that said, let's get started with today's presentation. So, a brief outline of what we're going to be talking about. We'll start with a very short introduction to SEM and electron imaging, just to go through what signals we're looking at and what we can expect to see in the different images and the different acquisition modes. And of course, we want to use the SEM as an X-ray analysis tool. We'll look at what signals we get and how we analyze them, what information we can extract. We will apply that to X-ray mapping and get to the point of all this, spectrum library matching. And mapping and library matching will tie in together and apply it to an actual sample. And in this case, it's going to be a brake pad. So with that said, SEM and electron imaging. Most of you will probably users or at least have knowledge of scanning electron microscopes or SEMs, and they are becoming quite prevalent tools at this point. It's no longer just academia and imaging tools. We find them in a lot of different industries, both for research purposes, but also for quality control, failure analysis, quality assurance, in drilling, mining, oil industries, pharmaceuticals, insurance companies even, I've had some interactions with. So it's a very common tool at this point. But it's not just an imaging tool. The signals we see in the microscope are primarily secondary electrons. That's the basic imaging tool in most microscopes. If not secondary electrons, you will typically have backscatter electrons as your basic imaging. Besides the electron imaging, we also generate cathode luminescence from some samples that we can image in the microscope. It's not as commonly used as the electron imaging, but it's definitely worth mentioning, and it has some specific applications. So these are mostly the imaging signals. What we are interested in is the X-rays coming out from the samples as we expose them to the electron beam. And given that EDAX sell both EDS, WDS, and EBSD detectors, we should probably also mention diffracted electrons. If you have crystalline samples, you can get diffraction of the primary electrons coming into the sample that we can record, which will give you information about the crystallography, orientation, and different crystal parameters. So the way the microscope works is that we have a very finely focused beam of electrons coming down onto the sample. And we let that beam dwell on different spots for a very short period of time and collect the signal we are interested in, which can be any or several of the signals we mentioned just now. And once we're done with that spot, we move over to the next one, collect the signal again, move over, and so on and so forth, until we have scanned the entire field of view and build up an image like that. So it's not like a standard optical microscope where you acquire your full frame of view in one go. It actually rasters or scans across and does it spot by spot. So if we have an illustration here of our sample, and we have a beam of electrons coming down, these electrons are going through an acceleration field inside the electron column before they actually hit the sample. We have a source of electrons up on top in the column. There's different types of sources, but in principle they work like an old-fashioned TV. You have the cathode ray tube TVs, where you have an electron source at the back, and then we have some different fields that we apply to them to move the beam around and accelerate it. The typical acceleration voltages are about 300 volt to 30 kilovolt. And since it's an electron we're putting down through the acceleration field, that means we have an energy in the range of 300 electron volts to 30 kilo electron volts when we hit the sample. There are some specialized SEMs where you have above 30 kilovolts, but 30 is typically the high range. And some of the newer electron microscopes, you can do imaging quite far down to, say, even 30 volts. But that's, again, specialized applications. So we have our beam of electrons coming down and hitting the sample. And the primary signal that we use for imaging is typically secondary electrons. A secondary electron detector illustrated here on our left-hand side. Typically, it's an Everly-Thornhart type where we have a field in front of the detector. Since the electron is a charged particle, we can basically suck it up with a positive voltage. The secondary electrons are typically defined as any electrons that have less than 50 electron volts. So that's significantly lower energy than the primary electrons coming in from the beam. What happens is that the primary electrons hit the material that's in the sample, interact with it in different ways, generate new electrons, lose energy, and anything that comes out from the sample again with less than 50 eV is defined as a secondary electron. Since the energy of these secondary electrons is quite low, they are strongly absorbed or attenuated in the sample. So that means that even though we can generate secondary electrons quite far down into the sample, several microns down, they will be absorbed as they try to escape. So we only get secondary electrons escaping from quite close to the surface. And that means they primarily give surface information and topography in the image. The other imaging technique, backscatter electrons. For that, we insert a backscatter detector. It's typically a ring that you insert right below the column or right above the sample, with a hole in the center where the electron beam can pass through. Backscatter electrons are high energy electrons. They have energies that's close to that of the incoming electron beam. What happens is that you have an electron coming down, and if it hits a nuclei in the sample, basically straight on, it will bounce back. So it doesn't really penetrate that far down into the sample, but it bounces back. And the larger the nuclei in the sample is, the bigger the chance of it being hit and the electrons bouncing back. So larger nuclei is typically the heavier elements, so heavier elements will show up brighter in the backscatter signal. The reason we insert the backscatter detector right above the sample is that backscatter electrons typically come back quite close to the incoming electron beam. So we need to be close to the incoming electron beam to actually pick them up. But backscatter electrons will primarily give us information about the sample composition. Then we move on to X-rays, which is what we are primarily interested in. X-rays are generated due to transitions in the electron shells of the atoms in the sample. Basically, we hit the electron shells with one of the incoming electrons, and we knock out an electron, so there's a hole, and we have a transition within the atom where we get a photon out in the X-ray energy range. And those photons we pick up with our X-ray detector. There's typically generally two types of X-ray detectors, EDS and WDS, where EDS is energy dispersive spectroscopy and WDS is wavelength dispersive. Both have their advantages and disadvantages. The most common one by far is EDS, and it has the advantage that you collect the full spectrum in one go. Compared to the WDS, where you measure wavelength by wavelength. Having an optics background, I basically think of them as a spectrometer and a monochrometer. So the WDS is much slower to acquire than the EDS, and typically only look at individual peaks in one go. But it does have significantly better resolution than the EDS on the given peaks. But we're going to stick to EDS today, at least. And we analyze these X-rays coming out from the sample, and because they are corresponding to specific transitions in the atoms they originate from, our X-ray signal gives us a lot of compositional information about what's in the sample. So if we look at what we actually learned from it. On the left-hand side, we have a backscatter image. You can see that we have different contrasts in this image. Some particles are brighter than others, which generally indicates they have a higher atomic number. We have larger nuclei and thus get more backscatter electrons from those regions. If you look at a basic EDF spectrum, we typically collect that as the electron beam raster over the sample. And the basic EDF spectrum is pretty much a sum of the signal generated in each spot that the electron beam rastered across. So we can have the image up on the screen, and the beam is rastering across, and we can collect the EDF spectrum at the same time. The EDF spectrum we see here, there's a bunch of peaks in there, and there's some background, and we can go in and analyze this. The background is what's called Bremsstrahlung. It's basically the electrons coming down through the sample that's being slowed down. And as they're being slowed down, they emit a continuum radiation, and that's the blue line we see down the bottom in the spectrum that we can model based on the composition and the actuation voltage we're using. Then all the peaks we see above are originating from the transitions we have in the elements in the sample. So we can assign these to specific elements. We can see in the low energy range, we have a couple of strong peaks from carbon and oxygen. We have some silicon and sulfur as we move up, and just a little above the middle, we have barium, where you can see we have 3 peaks from different transition in barium. With this spectrum, if we make a few assumptions about the sample, basically we assume it's flat and it's homogeneous, it's thick, we can calculate the composition of the sample that corresponds to the spectrum we acquired. And we can see here that this sample shows up primarily being carbon and oxygen, with a lot of other different elements in smaller concentrations in there. So the basic EDF spectrum shows us what we have in our sample. And if we do quantification on it, it tells us how much of the different elements we have. What it doesn't tell us is where we find the different elements. If we look at the backscatter image, we can quite clearly see that this is not a homogeneous sample. We have different particles showing different contrast. So we wouldn't expect these elements to be scattered uniformly throughout the entire field of view. So that's where we can apply elemental mapping. In the basic spectrum, we just sum up throughout the entire field of view what X-rays are coming in. When we do the elemental mapping, we acquire in each individual pixel for a set amount of time and collect a spectrum there. We can run this several times to build up statistics, but the basic idea is that we have a full spectrum for each pixel. And based on the peaks in these spectra, we can plot their height in a color scale, which corresponds to the composition or the concentration of the different elements, and we can plot that as a map. So here we see the barium map for this sample, and we can see there's a pretty decent match between the bright particles in the backscatter image and the barium on the right-hand side. If we take a look at the sulfur map, we can also see that there's a strong correlation between the barium and the sulfur, but not completely. There's a sulfur-containing quite large particle in your lower left-hand side corner, which corresponds to a slightly darker particle in the backscatter image, where we can see if we compare to the barium map, there's no barium found in that particle. And we can also see we have a high sulfur-containing particle around the middle of the image to your right-hand side. We go in and look at aluminum. We can see there's a bit of that as well. Quite low concentrations, which is why this image looks slightly more noisy. But there's a few particles around where we have high aluminum concentrations. And if we look at the oxygen map, we can see the entire sample is basically oxidized. There's varying concentrations, but we find oxygen throughout our entire sample. So our elemental maps show us how the individual elements are distributed. But often we're not necessarily interested in the distribution of any one element. What we most of the time want to know is what's the relationship between the elements. As I pulled up the different maps before, I could start to see that, oh, this particle in the lower left is high in sulfur, but there's no barium, as opposed to the other brighter particles that have barium and sulfur. So we could do all these overlays and try to figure out what's the composition and how do these different elements relate to the different particles. We could also apply phase mapping. So phase mapping is a way to bring out this information without having to go through and overlay all the maps. The way we do it is that we take a spectrum, of course, a normal map throughout the entire region at each individual pixel. But to build a phase map, we compare the spectrum pixel by pixel. And if they are similar to some degree, we assign them similar colors. So we look at the spectra, not the map overlays, but the actual spectra from the individual pixels and determine, are they similar, should they have the same color. Basically, we do a chi-square fit or comparison, pixel to pixel, and if they are above or below a certain value, we give them the same or different colors. As we build up statistics in the spectrum, this threshold of when we assign different colors change, so we can start to separate out more and more phases as we build up statistics. And we can see that the different particles in the backscatter image are assigned different colors on the right-hand side. If we go in and take a closer look at this phase map, pull out the spectrum, we can see this gold-colored phase. We saw from the overlays that we had barium, sulfur, and oxygen in this phase, and that's what the automatic routine has used to identify this phase. There's strong barium, sulfur, and oxygen peaks. And all the yellow pixels or gold-colored pixels that we have assigned over here will have similar characteristics. If we look at the barium map, we can see that there's a good correlation between the gold-colored phase and the barium map, but it's not complete. That there are some areas where we have barium that's not in the gold-colored phase. For instance, the red phase in the phase map corresponding to the bright barium particle in the lower right corner. So if you look at the spectrum from the red phase, we can see we have still barium, sulfur, and oxygen, but the ratios have changed. There's less sulfur and less oxygen in this peak, thus higher concentration of barium. And we also see some potassium and silicon in here that wasn't present to the same degree in the gold-colored phase. So the phase map goes in and compares these two spectra and assigns them different colors based on not just the presence of elements, but also how much of it is present there, but still without going in and doing a full quantification. It is simply a spectral comparison routine. If you look at the silicon map, we can see not too much silicon, but we do have it spread around in particles in the sample. And if you look at this brown phase in our phase map on the lower left corner, we can see it does have some amount of silicon if we compare it to the silicon map in green, but it's quite low in barium if we look at the barium in the lower left corner, the barium map. So if we go in and look at the spectrum from that phase, you can see here in the brown phase we have strong strontium, silicon, and sulfur peaks, which again is different from the red phase and thus is assigned a different color. So the essence of it is that phase mapping is an automated routine that groups together areas with similar composition. It doesn't go in and look at all the different elemental maps and try to match them up. It simply groups the different pixels based on what elements do we have in there, how does the spectra look. So, spectrum library matching, what is it? Well, the way we like to think about it is a quick and convenient method to identify compounds present in the sample. When we looked at the basic EDF spectrum, we were looking at elements, but the way we often use the library matching is to find compounds. And the way it does it is that you build a library of reference spectra of your compounds, and then you can match it to your unknown spectrum that you pull up. And the reason for doing this is that it speeds up your process significantly. You can identify materials or compounds without having to go through a lot of data interpretation and calculations and have to memorize a lot of things. So for instance, what do we mean by interpretation? We have this spectrum. Quite simple. We have iron, oxygen, and a bit of carbon in there as well. If we quantify this spectrum, we'll get something like this. We have 57 atomic percent oxygen roughly and 43 atomic percent iron. And that is roughly a 4:3 ratio of oxygen to iron. Before anybody posts questions to the Q&A, what happened to the carbon? That is because this is a carbon-coated sample. I have applied a carbon coating correction. So in this case, we have about 42 nanometers of carbon on top of the sample. That's included in the calculation, and that's why we see 0 weight or atomic percent down here for carbon, even though we can clearly see a carbon peak in the spectrum. So that's a routine we can apply to our quantification when we know that carbon is not part of the material but a coating on top, and we can pull that out. But oxygen to iron ratio 4:3, and if we have a bit of background knowledge and we know our iron and oxidation states and so on and so forth, we could conclude that this is probably magnetite. But we would have to go through and realize 5743 corresponds to a 43, and we would have to know the composition of magnetite. So that's what we mean with analysis, and a bit of background knowledge is needed to identify compounds. So how do we make that easier with library matching? Well, the matching routine reduces the time and the knowledge that we need to identify these compounds by basically making a push button approach. And the first step to this push button approach is to build a matching library. We have a short video to show you how that's done. Unfortunately, I can't run this on desktop shared screen so you can see me doing it live, but we acquired a video of it. The sample that I used to build the library in this case was an SPI standard sample of 53 mineral standards. And here we should have the video. This is the team software in my Spectrum view window. I have Spectrum matching open on the right-hand side. Click the search button that brings up my match library builder. I'm in my user profile, and I see all my projects here on the left-hand side. The one I want to use is my mineral library. I'll just select that. I can go through and filter all the data I have in there based on date and element presence and concentrations and what acquisitions parameters I used. But for now, I just want everything in there, so I just click search, and it shows me all the data I have for that project. A couple I don't want, so I'll just remove those. So I have a list of my standards in here that I acquired Spectra from. Go in and hit save. Name to the library, like that, and hit OK. And we can now see that it loaded up the library in my team software. I have this folder button. I could click that if I wanted to load up a different library that I had saved earlier. So I can go through and search my previous projects and build libraries based on that. And the library is just saved as a small file, so it's quite easy to share that between users or facilities if there's multiple facilities. One user can build a library file and share it with the other facilities, so everybody's using the same thing if that's needed. So we now have a library file built, and we can go in and apply it to our spectrum now. So here's my magnetite spectrum. I go in and open up my spectrum tools, and you can see I have my search button that I use to create the library. I have some match options here, whether I want to do a chi-square on the spectrum or I want to do a chi-square on the concentration, the quant numbers. So now we'll do it on the spectrum. I can adjust my match sensitivity. go up and down. This is basically a cutoff filter. Anything below the confidence that I set will not be shown. And I have my match button. So if I click my match button, what I get is the 3 best matching spectra found in my library corresponding to my unknown spectrum. And in this case, it shows up with a match for magnetite, hematite, and ilmenite. 100% match for magnetite, 92.1 for hematite, and 61.12 confidence for the ilmenite. So just by the click of a button, I can see what's the compound that corresponds to the spectrum. I don't need to go in through my quant. I don't need to remember that magnetite has this composition, and I don't need to do the math on my quant numbers. 57 and 43 corresponds to 4:3 ratio, and realize all these intricacies of the analysis. So I cut down the time significantly, and I get a confidence level of the match to the compound. So let's apply that to an actual sample. We used our Hitachi S3400N microscope. It's in variable pressure mode for this analysis because the sample is our brake pad. See, this is the same image as I showed you before. Brake pads are not exactly conductive, and that's why we need the variable pressure mode. I'm running this at fairly high current, which is why this image is looking slightly blurry, and we could probably have done that better, but we're not really interested in the imaging for this. We're interested in the X-rays. I collected a map at 1,200 times magnification at 20 kV, 200 microseconds dwell time per pixel, and 256 by 200 pixel size of the map, which corresponds to about 10 microns per pixel. So each pixel is about 10 microns wide. I let it run for 90 frames, which if we start multiplying 256 by 200 pixels, 200 microseconds per pixel, 90 times, that comes out to just about 15 minutes acquisition time. So it's not an extremely fast collection time, but it's not days either. This is reasonable collection time in most labs. And another reason for using the Hitachi microscope is that this is a full brake pad. It's not a cutout, it's not a segment of it. We actually fit a full brake pad in there. And it's used at that, so there's a bunch of contamination and other stuff on there. So this is close to a real-world sample. So what do we get? Again, backscatter image on the left. And when we collect maps in the team software, we get not only the elemental maps and the phase map, we also get a CPS map, or counts per second. What this map shows us is basically where do we get X-rays from. So brighter particles are things that have higher X-ray yield, and darker areas are where we don't see as many X-rays. I often compare my CPS map to my backscatter image if I'm in backscatter mode, because in backscatter mode, light elements show up dark. So carbon will usually be dark in a backscatter image, but carbon, you'll still generate X-rays from carbon. So in the CPS image, carbon will show up as not bright, but still fairly light shade of gray. But we can see here on the top right corner, we have a couple of darker areas, and these also dark in the backscatter image. So this is most likely shadowing or voids into our brake pad. So we have a couple of holes there where we're getting lower X-ray counts from. We can see one of the particles is basically completely black in the upper range, meaning we don't really get any X-rays from that region at all. So this is also a slight warning that your statistics will be poor in that area because you have very few X-rays escape. So CPS map, and we get our phase map where it groups together the different phases. Now that we have the phase map and the sum spectrum, that's what you'll see once the acquisition is done in the team interface. You have an idea of what elements you have in the sample based on the sum spectrum, and you have an idea of the distribution of areas with compositional differences by looking at the phase spectrum. But to apply our phase mapping, or sorry, spectrum matching to this, we need to know what's the spectrum of each phase. And that's quite easy to do in the team software, to extract the spectrum from all the pixels that are in any one given phase. Short video again to show how it's done. I have here my pie chart on my left-hand side with my different phases. I'll go in and select the gold phase, brings up a new pie chart with the elements identified in the phase, and I click my center button here, and that brings up the sum spectrum of all the pixels in the gold-colored phase. So I can quite easily extract my spectrum information from any given phase. Now that I have the spectrum extracted, we can apply our library to it. So this is the spectrum. And as you saw before, I'll go in and hit my match button. And I'll get free matches, or the top 3 matches for this the spectrum that's above my threshold for the match sensitivity. In this case, you see the gold phase is barite with 89.16 fit confidence. We look at the brown phase and do the same thing. We get celestite. And if you remember what I showed you before, we saw strontium, sulfur, oxygen, and the reason why we are not getting 100% is that we have other trace elements in here as well. We thought there was some silicon and potassium when we're looking at the map overlays. But in general, this matches up quite well with celestite. And we can go through and extract these different phases and match them up. So we can see gold is barite, the brown over here is celestite, we have pyrogarnet, quite low confidence it seems, but still reasonable, and we have benitoid. Pretty sure I didn't pronounce that correctly, hence my disclaimer in the beginning. So we can go through all these phases and analyze what's the, not just the composition, but what compound does it match up with. We'll just run through one more example, different region of the same break path, slightly different collection conditions, 350 times magnification, 15 kilovolts now, 200 microseconds dwell time, 512 by 200 pixel size. Sorry, that should have been 512 by 400, which is again roughly 20 microns pixel size, and collected for 83 frames. So this one is collected for twice the amount of time, but you can also see we're zoomed out by roughly a factor of 4, so we're imaging a much larger area at this point. If we again go in, we look at the backscatter image and compare it to the CPS image, and now you can clearly see what I was talking about before. In the backscatter image, we have quite a few completely dark areas. The entire top right corner is dark, but look at the CPS map where it would show up as just a different shade of gray. So this is most likely carbon showing up, or at least the light element showing up dark in the backscatter, but we still get a significant extra yield from the region. And we can see we also have a void in our sample, about the lower middle, that shows up dark in our CPS map. We get a phase map. If you look closely, you can see the dark region in the CPS map is a little noisy in our phase map. And that's simply because we get lower X-ray counts from that region, so our statistics are worse in there. And we can go through and do the same thing. Carbon, we don't need to do a match on that. find a stibnite particle down here in the lower right corner, quite high confidence. Still see our barite here in the blue phase. We find a magnetite particle in there as well. The celestite again, some amaldine garnets, and benitoid. So by extracting the spectra from our phases and matching it up to our library, we can quite easily go in and identify not just the composition, but the actual compound that identifies that region. Now, I used a mineral standards library here, so I wouldn't really expect to get great matching results, since break pads are not necessarily made up of these 53 standards that we collected from. And again, this is a used break pad, so you'll have a lot of contamination and smearing of the different zones. It might have been heated up, have some diffusion, so our compositions don't match up precisely anymore. But if we had built a library dedicated to this, if we knew what compounds to expect in a break pad, we can build a dedicated library and have much better match precision and matches for more phases. You'll notice I didn't match all of the phases in here. Some of them are variations of the barite in this case, where we have different inclusions of primarily silicon or potassium in this case. Even if we didn't have a full match, we could still use the information from that. We can go in and, for instance, do a different spectrum, subtract the barite from the unknown spectrum, and see what's left in there. Is it a mix of two different compounds we're seeing? So even though you don't have a perfect match, you'll still get a lot of information out from the matching library. So what do I want you to take away from this, and what did we actually go through in the presentation? Well, we showed that by applying phase mapping and spectrum matching, in this case to a break pad, we can easily identify the different phases and match the compounds in there. So the idea is that we're not matching, we're not just getting the composition, it's so many atomic percent oxygen or iron or whatever else we have in there, but we actually get an idea of what compound it is. We also showed that you can build a matching library based on any spectrum that you have in your team software, team database. So if you have your data already acquired, you can go back and search through it and build a library quite easily based on that. You could even go back and add everything in your database into a spectrum library and match that up against your unknown spectrum if you're in one of those situations where you know you've seen the spectrum before, but you can't quite remember what sample was it. You'll be able to do that, and it will tell you this sample matches this spectrum. So basically, phase mapping, we use that as a tool to identify areas of similar compositions. Spectrum matching can be used as a tool to identify the compounds that match those compositions without having to go through the details of the ratios and have to look up what different compounds do you have that would match up to those ratios. And the combination of phase mapping and spectrum matching is a very powerful tool, in my opinion, that can reduce the time it takes to analyze samples significantly, especially if you're running the same type of samples where you can build up a library that will cover most of what you're expecting to see. And even though sometimes it won't match your library, but then you'll have that information that this is something I haven't seen before and can go in and do the additional analysis. We are seeing use for spectrum matching quite a few different areas already, even though it's a fairly new feature. And some of these are contaminant analysis. If you have a process where you have the risk of contamination throughout the process, you can build a library of the potential contaminants. When you get a contaminated sample back in, you can acquire the spectrum and quite easily match it up to your known contaminants and figure out, okay, what is this, what compound is it, and thus where in the process was it most likely contaminated. We're also seeing some use in reverse engineering, where you take a competitor sample and try to figure out what did they do and what did they put in here. Quality control as well. You could go through and compare all your quant numbers and look at how much does it deviate, but the spectrum match can be used as a quick pass-fail test on your fit confidence, basically. In this case, you'll most likely do it on the quant numbers and not just on the spectrum, the match that is. Or we build a mineral library here. Mineral analysis is another of the big areas where we use for the spectrum matching and the combination with. So with that, I would like to thank you for your attention and go into the Q&A and look at what we have here. Sorry, it will be just 1 second while I bring up the different. I'll read the different questions. Okay, there's a question about the oxygen in the different phases. Let's see, it's this one out. Let's see. So here we have the pyrope garnet, and the question is, how do I know what the oxygen is bound to, basically? That is bound to the silicon and not magnesium or aluminum. The quick answer is, I don't. This spectrum was, my match spectrum, I do know how it's bound. My match spectrum in the library was acquired from a mineral standard. So this is one of the typically NIST-approved standards where you know the exact composition of the element in there. So I go in and acquire a spectrum from the sample that I know is a pyrope garnet. I know the exact composition. So I know this is the exact spectrum from a pyrope garnet with this chemical composition. I then use that as an input parameter in my match routine. So it matches up with 66% confidence in this case, which tells me this phase is probably not straight up pyrope garnet. I will probably have to go in and analyze this a little further, whether it's just because there's contamination as well. If I have carbon on top, that will throw off my match. Or if it's really because my spectrum library is incomplete compared to this sample. As I said, we're just using some minerals standards here, which might not be the best library to apply to a brake pad that's been used. But if you have the right library for your application, you'll have quite good indication of what's the compound. So the brief answer in this case, I know that it's bound to the silicon because that's my standard, but I don't know that it's bound to silicon in this exact sample. There is another question, whether we can apply this to the desktop microscope. Yes, we can. It's the spectrum matching is a licensed feature for the team software, but we can apply it to basically any detector, EDS detector that comes with the team software. So desktop, benchtop microscopes, we can apply this as well, as long as we can mount a EDS detector on the system. There's a few options for different EDS detectors. There are some that are pretty much dedicated to the benchtop systems because they are smaller. You don't necessarily have the ability to mount a full EDS system on there, but there's options for that as well. There is a question about beam skirting in variable pressure modes, how it affects the X-rays and the spectrum. I set for my analysis that I used variable pressure mode in our SEM, and variable pressure mode basically means that we are running the sample in a dirty vacuum. We let a little bit of air into our analysis chamber, and since we have higher molecule density in there compared to a high vacuum, we see more scattering of the electrons that are coming down through the column. And this can have a significant effect on the spectrum. Should be a little careful when we're applying variable pressure mode, because you can get signal from areas that are quite far away from what you think you're looking at. It is not a huge problem though, because you can figure out how much does this affect by changing your pressure slightly. The effect of the beam skirting is fairly linear. So if you double or half your pressure in the chamber, you should be able to see how much does it affect the spectrum. In the next iteration of the team software, we'll probably include a option to measure two spectra at different pressures and then extrapolate from that what is the effect and calculate back to what would your spectrum be if you didn't have the variable pressure mode. There's another question about the beam size and the focus. How does that affect my X-ray quality? That one is a little tricky. It depends on what size features we're looking at. The X-ray quality isn't affected really by the sharpness of the image. Our X-rays will still be generated. We'll get the same amount of counts whether we're in focus or not. What will change is the spatial resolution of our X-rays a little bit. In most cases, it doesn't matter too much. The map I acquired here were like 10 or 20 micron pixel width, which is less than the resolution limit of the X-rays. But for instance, if you go to very low acceleration voltages, you can see a significant effect of the beam size. The basic, what we usually say is that the X-ray spatial resolution is much worse than your SEM resolution. Typically, you get X-rays from a cubic micron-sized area, and you can see nanometer-sized particles, so it doesn't really affect much. But if you go to very low acceleration voltages, you start to see some of these effects, where in principle, you'd have much better X-ray resolution because you're getting your interaction volume is shrinking, but your beam size will actually play against you in that. So if you go to low acceleration voltages, you can see some effects of the beam, the spot size. But generally at high acceleration voltages, you're limited by your X-ray interaction volume and not the beam size, the sharpness of the image. There's a question about if you have the SPC files from another project and you want to use that in your library. In the team software, if you open up your Spectrum window, you can basically drag and drop your SPC files directly into that window. And if you have multiple files, it will ask you if you want to add them to your project as well. So you would add them to a project. So you have the Spectra saved as part of a project, and then you can go into your search function under Spectrum Matching, select that project, and pull out your Spectra that way around and build a library using that. There is another question about, I mentioned that I applied a carbon coating to my sample. There's a question of whether we can apply other coating material corrections. Right now, the answer is no. It's something we have been discussing a little bit. Often people gold code or gold palladium code their samples to get nice imaging. That has some not so nice effects on the EDF spectra. Gold is strongly attenuating compared to carbon, so you will have to apply much, much higher correction factors, which will induce higher error rates in your statistics if you use gold coding. So we have not included gold coding corrections at this point, but we're discussing whether it is something we want to include. The danger is, of course, that even though we correct for it, we still potentially introduce uncertainties in our correction factors. Simply, we are correcting for something, and that will introduce statistical deviations. So even if we apply our correction factors, we will potentially throw off the quant numbers a little bit. And we don't want people to go out and have complete confidence that, oh, I applied a gold correction, so now I can do my analysis down to 0.1 weight percentage of carbon or any other light elements. But we might include it in the future. It is up for discussion. There's a question about how low can we go, basically, in high voltage. Whether we can apply it to polymers. The quick answer is yes. We can go quite low. We can apply it to polymers. But that immediately brings a follow-up question of what do we want to see? When we go to low actuation voltages, we are limited in the lines of the elements that we can excite. So basically, if we're looking at silicon, the silicon K line is at 1.74 keV. And the absorption line is slightly above that. So in general, if we have anything less than 3 keV coming down, the silicon K line will be so poorly excited we won't get much of a signal. And as you go down in actuation voltage, you lose more and more elements that you basically can't excite them. You won't have good enough signal or statistics to do analysis on them. I have done EDS acquisition down to, I think the lowest I've done is about 500 volts. And we can still get signal in those ranges, but you're quite limited in what you can see. Basically, it will be carbon and nitrogen. 500 volts, you're below the absorption line of oxygen. 800, you might be able to see a slight peak at oxygen as well. So what elements you can see is one thing to take into consideration when we're talking about low actuation voltage analysis. The other thing is how much current can your microscope deliver in those ranges. The EDS count rate, the number of X-rays we generate, is partly dependent on the actuation voltage and partly dependent on the electron current. As we go down in actuation voltage, we'll generate fewer and fewer X-rays. So typically, you would go up in beam current to compensate for the loss of X-rays. But when you're down that low, you'll probably be hitting the limit of how much current your microscope can deliver. So yes, we can still analyze it. That's not a problem. But your acquisition time will usually go up quite significantly in order to get a good signal. And depending on how beam sensitive your sample is, polymers are typically quite beam sensitive. So they won't do well with high beam currents. The answer is to increase your acquisition time, to reduce the dose, or basically the intensity, and hopefully you'll be able to get a good spectrum still. Whether there's any libraries for polymers, we do not build and sell libraries just yet. It's something we might consider doing if there's a market for it, if there's an interest in it. Right now, it's more meant for people to build their own libraries, but we might consider building some of these standard libraries or work with external partners to build these libraries so we can make them available to the different markets. There's a question about how low can we go again, but this time not in extraction voltage, in our concentration. Whether we can detect compounds with about 1 atomic percent. And that is a tricky question to answer because it heavily depends on what element we're talking about. If we're talking about heavy elements, where we get good line separation and good X-ray counts, then the answer is yes. 1 atomic percent can quite easily give us a good EDF spectrum. But if we're talking about 1 atomic percent of boron or carbon, then it gets much more challenging. So it depends on the element and it depends on the sample composition. But yes, we can do matching in the low concentration range, but it does depend heavily on the sample in question. Let's see. There's a question about the accuracy of the EDS measurements. Again, that highly depends on your sample. I mentioned when we do our quant numbers, we have a few assumptions we make about the sample. Number one is that it's perfectly flat. Number two is that it's completely homogeneous within the interaction volume. And number three is that it's infinitely thick to the, as seen from the electron beam. And if you're outside those assumptions, then your reliability goes down. If you have carbon on top of your sample, if it's contaminated any kind of way, we will be correcting as if carbon is throughout the entire sample. And we will be applying a correction that's not necessarily real. So in this case, your numbers will be thrown off. So to get the perfect analysis, really push the limits, one thing is you need to satisfy those conditions. The other thing is you need good statistics. You have to have a lot of counts in your spectrum to get a good quantum number and a good reliability of those. It comes down to the statistics, basically. And especially in the light element range, that can be a problem with the correction factors. If you do your quantification and look at your staff numbers, CAF, that's basically the correction factors that we're applying. And you can see in the light element range, we apply a higher correction factor. So light element range is more sensitive to these corrections. And if you have any kind of contamination on top, you will get stronger attenuation in the light element range and thereby throw off your quant numbers. So the accuracy, that depends on the sample, how well it meets our conditions, and to which extent you have enough statistics in your spectrum. If all those things are correct, you can get quite high reliability, but you have to meet those conditions for the ultimate precision. I am being told by Sue that we are running out of time. So that's all the questions we have time to go through at this point. But I have a log of the questions, and I believe I should have your email addresses as well. So I will follow up with the remaining questions by email. Probably won't be today, but I will get to you and answer your questions. So with that, I will like to say thank you for joining the webinar today, and I hope you got something out of that. Okay, have a nice day. Bye.